Now there's something else I want to make a note of here. Think about this instant in time. That was before the block started moving, and so what was the relationship between the force with which you're pulling on the spring scale and the friction force? Well, they're equal, right? Because it's not moving, therefore it's not accelerating, so the net force is zero, and they're balanced. Now what about here? The same thing. So all throughout this time, the friction force is increasing before the block starts to move. That's because static friction is what we call a smart force. And a smart force in physics is one that's a force that's the magnitude that it needs to be to keep everything at equilibrium. The other force that we've learned so far that's a smart force is the normal force. If you think about it, how hard does the table push up on a box of books? Well, equal to the weight of the box of the books to keep it at rest. If you put another box of books on top of that and double the gravitational force, then as long as the table's strong enough, it's going to double the normal force to support both boxes of books. And so these normal forces are as great as they need to be to keep equilibrium. And static frictional force is a smart force. And that's why you saw the tension in the spring increase as you started to pull, as the friction force increased to keep it at rest, until finally you pulled so hard that the friction force couldn't keep it in place any longer and it started to move. Right now, I also want you to imagine a graph. We varied the normal force and we want to look at how that affected the friction force. And so let's imagine graphing the friction force as a function of the normal force. Well, the resulting graph, as you saw in the experiment, is one of a constant positive slope. In other words, for the same two surfaces, we're going to have a friction force that's directly proportional to the normal force. And so when you started adding masses to the top of the block, you saw that the friction force required to both move it and to keep it moving at a constant rate increased. Well, the slope of this line is a quantity in physics that we call the coefficient of friction. And the coefficient of friction is the ratio, then, of the normal force to the frictional force to the normal force. It's a property of the two materials, and it's the slope of this line. And so imagine another two surfaces that are rubbing next to each other that have a slope like this. Well, for the same normal force, it has a higher frictional force. And so it would have a larger coefficient of friction. And typically things with high coefficients of friction are rough or sticky. Similarly, something with a low coefficient of friction is something that has a smooth surface, or two surfaces that are smooth, relatively smooth to each other. And slipped up there, but what I want you to make sure you remember is that the coefficient of friction is between two surfaces. You can't say that a box has a coefficient of friction. It's only the box and the table, or the box and the floor, that you can talk about having a coefficient of friction. It's got to be the two surfaces that are trying to slide relative to each other. And you've seen this experience in your own everyday life. If you're pushing a box on a hardwood floor, it's much easier to move than pushing the same box with the same weight on a carpeted floor, because the coefficient of friction between the box and the carpeted floor is much higher. So therefore, for the same normal force, you have a much greater friction force. And so this coefficient of friction quantity has a symbol. It's the symbol mu. It's the Greek equivalent to our letter M. And it looks a little like a U with a tail, or I like to describe it as looking like a mullet. But this mu is the symbol for the coefficient of friction, and you can guess that the units for the coefficient of friction there are none. It's a dimensionless quantity because it's a ratio of two different forces that are measured in newtons, and so newtons divided by newtons gives you no units. And so it's a ratio, and it's given the symbol mu. Now, what that means is if I take the y-axis quantity, which is friction, and the x-axis quantity, which is the normal, and then I write it in slope-intercept form, for kinetic friction, it's going to equal mu times normal. So the coefficient of kinetic friction times the normal force will tell you the kinetic friction force. Static friction, on the other hand, as we mentioned, is a smart force, and so it doesn't have to be equal to its maximum value, and so it can be less than or equal to the coefficient of friction times the normal force. And so these equations oftentimes will combine in one, and we'll say that friction is less than or equal to the coefficient of friction times normal, and of course the difference being whether or not it's kinetic or static, which you saw in the experiment. All right, so finally I want to go back and pick up the problem that we worked in class the other day without friction, and this time I want to add friction. And so we've got a box on a 30-degree incline, and I'm just going to give the box a mass m. I'm not going to worry about what the actual quantity is. And I'm going to draw a free body diagram. I'm going to label all the forces acting on the box. There's of course mg directed towards the center of planet Earth, which normal people call down. And there's a normal force that's perpendicular to the surface of the incline by definition. And then now we have a friction force, which is up the incline because it's resisting the motion of the block down the incline. Well, now that I've drawn all the real forces acting, now I want to define my coordinate system, and according to rule 1, if there is an acceleration, which there is in this case, we want to make it along an axis. And so I will make the x-axis along the incline. That rotates the y-axis to perpendicular to it, which is the direction of the normal force. And I'm going to say up is positive, even though it doesn't matter whatsoever. And I'm going to make down the incline positive. Well, of course, mg is in both directions, and so I want to break it down into its components. I'm going to call the horizontal component mg times sine of 30 degrees, which if you don't see how I did that, you'll want to look back at the previous videos to see that trig in slow motion. And this component is mg cosine of 30 degrees. So those are the components of mg. Now I'm ready to write my fnet statements. If I do fnet let's do fnet in the y direction first. Fnet in the y direction equals, I've assigned up as positive, so it's the normal minus mg cosine of 30 degrees. All the motion is along the horizontal axis, and so therefore the acceleration in the y direction is 0. And that tells me then n equals mg times cosine of 30 degrees. Now, last time we did this, we didn't need that, but as you saw from the experiment, the friction force, which we have now, depends on normal, and so we needed to do that step. All right, changing our thoughts to the horizontal direction, the fnet in the horizontal direction is, of course, down the incline is mg sine of 30 degrees. Let me get rid of this now that I'm done with it so that it doesn't get in the way of this that I'm drawing here, minus the friction force. Well, what does fnet equal? It always equals ma, and so fnet equals ma in the horizontal direction means mg sine 30 degrees minus friction. Well, this thing is sliding, and so it's kinetic friction, and so what does friction equal? It equals mu times normal. And I apologize, in my rush I didn't tell you what the coefficient of kinetic friction was for these two surfaces. The example I used in class was 0.2, so we'll use that again. So back to work here. MA then equals mg sine of 30 degrees minus mu times normal. Well, what is normal? Well, this is what we had to do the vertical direction for, to find that normal is equal to mg times cosine of 30 degrees. Well, now all the terms have an m in them, and so I can divide through by the mass, take mass out of all of them, and so A equals g times sine of 30 degrees minus mu times g cosine of 30 degrees. And so now all that's left is to plug that in my calculator. G sine 30, of course, would be 5. And mu times g would be 2, times cosine of 30 would be like, what is that, like roughly 1.7? I'll just round it to 1.7 for now, which means that the difference is approximately 3.3 meters per second squared, and I should have left room to write the direction, which of course is down the incline. And so again, here you can see an example of Newton's second law where we have friction, where we need both directions because, as we learned in the experiment, the friction force depends on the normal force.